All right. So last time we talked about parametric equations, which were a way of expressing curves on the xy plane, but rather than being y as being a function of x, we now have x and y as separate functions of the third variable called t. And last time we saw what these equations were, and then also we practiced drawing them a bit or seeing how they looked. And fortunately, that was a little bit difficult because a lot of times we just have to plot points, and that's really kind of the best reasonable thing that we can do for those. Now, what we're going to do today, since this is a calculus class, is we're going to learn about calculus with parametric curves. So what we're going to do is we're first going to go over doing derivatives with parametric curves, and then we're going to go over doing integrals with parametric curves, kind of like the way we did Calc 1 with normal xy. Let's go ahead and get started. So let's say we have some kind of parametric curve. X of t is some function of t, and y of t is maybe a different function. Now, since these are functions of t, what we can do is we could look at dx dt, or x prime, and that will just be the t derivative of whatever function we have in there. And then the same thing, of course, will work for y. So dy dt will be y prime or g prime of t. Now, remember last time we had this sort of physics interpretation of these parametric equations. Remember, the x and y could represent the x and y position of a particle at a particular time. Well, if you've taken physics before, at least calculus-based physics, you know that if we do the derivative of the displacement, then we're going to get the velocity of our particle. So if you'd like to imagine this in terms of physics, this is our velocity in the x direction, and this is our velocity in the y direction. Now, note that both of these are actually different from what we usually try to find dy dx. dy dx can still be relevant for these curves, and it means exactly the same thing that it did in Calc 1. So if we have some kind of curve, this is going to measure the slope of the curve at a particular point. So we can still figure out what this is, even if we have functions like that. Let's say we wanted to know dy dx. Well, what I'm going to do is I'm going to sort of multiply the top and bottom by 1 over dt. And remember, these aren't exactly fractions, but in many ways they kind of work like them. So that means that this is still going to be equal to that. But then we just have y prime over x prime. So if we want to know what dy dx is in terms of t, we could just do the y derivative divided by the x derivative. And this equation also shows that these are not exactly the same thing. dy dt isn't the same thing as dy dx. They measure different things. Finally, one other way of thinking about these is that dx dt tells you how fast you're going back and forth horizontally, and dy dt tells you how fast you're going vertically up and down. All right, let's look at an example of this. Let's say I have x of t is, say, sine of t, and y of t is e to the t. Technically, for maybe at least a limited domain, we could write this as a function of x, but that'd be really complicated. It's actually going to be easier to do this. So let's say I wanted to know the derivative at a particular point. Let's say I was graphing this. Maybe I wanted to know the slope of the tangent line or something. So let's find dy dx for this curve at the point 0, 1. Now, remember, these have t's in them. They're not x's and y's on their own. So we need to get a t value to make us go through this point. Well, if we see what t makes sine be 0, that could be 0, pi, 2 pi, any multiple of pi. But the only thing that will make e to the t be 1 is 0. So since 0 is the only t value that will work for both of these, that technically means that we're going to be plugging in 0 once we get our derivative. All right, so let's figure out what dy dx is. Well, it's y prime over x prime, where I'm just going to reserve primes for t derivatives now. Y prime, the derivative of e to the t, well, that's easy. It's e to the t. And then down here we have the derivative of sine, which is going to be cosine of t. And then when we plug in t equals 0, we have e to the 0, which is 1, and cosine of 0, which is 1. So we end up getting 1 for our derivative. And remember, dy dx still means the same thing that it did before. So this curve, I don't know exactly what it looks like, but it does go through the point 0, 1, And when it does, it's going to have a slope of 1 as it moves through there. All right. Now, just in the same way that we could find the first derivative with respect to x, we could also find the second derivative with respect to x. So d squared y over dx squared. Okay, well, how are we going to figure this out in terms of t? Well, remember the second derivative is just another x derivative of the first derivative. So that's what the second derivative is. We have the first derivative, we take another one, that's the second derivative. Now we actually already have a formula for dy dx. Remember, it's just x prime over y prime. But remember that these guys, they're functions of t, and t has some kind of complicated relationship with x. So there'd be a kind of a nasty chain rule going on here. So what we could do to make things better is there's another way we can write the x derivative. We could write this as the t derivative times dt dx. Because remember, these aren't exactly fractions, but they kind of work in the same way. You can imagine these dt's canceling out, and then we would just get ddx. That's what I'm going to do here. I'm going to change this ddx to a ddt, and then that'll match up nicely with my x prime and y prime, which are functions of t, and then I'm going to stick this dt dx at the end. Okay, now, the thing is that dt dx is a little bit weird because usually we have x in terms of t, not the other way around. So what I'm going to do is I'm going to flip that and put it on the bottom. So I have d dt of x prime over y prime, and then all of this is going to be divided by dx dt, aka x prime. Remember, this is the second derivative. All right. Now, all we need to do for this, by the way, so this right here, this is a perfectly acceptable form for the second derivative, especially if this simplifies down to something nice. But if it doesn't, then there's kind of a more simplified, or another way of writing this. What I'm going to do is, oh wait, ooh, this is backwards. Y prime, x prime, there we go. So what I'm going to do is I'm going to take the t derivative of this, meaning that I'm going to use the quotient rule since it's a fraction. So let's see here. So on my bottom here, I have an x prime from this, and then here's my quotient on the top. All right, so I have the bottom, and that's going to be squared. Bring the bottom up to the top. Take the derivative of the top, so we actually have a y double prime now. And then I subtract where I leave the top alone, and take the derivative of the bottom, giving us an x double prime. And then finally, to simplify this fraction, I'm dividing this fraction by another x prime, so we can simplify this down to x prime cubed on the bottom. So essentially, this is like the quotient rule of our first answer with an extra x prime at the bottom. That's the way I remember this. So you can either use it in this form right here, if it's easier to do it that way, or you could use it in this form right here, which this is dy dx. So typically, my suggestion is to use this equation if dy dx is not a fraction, and to use this one if dy dx is a fraction. So dy dx is a fraction, is not. That's kind of my general rule of thumb, but either way will take probably about the same amount of time. All right, well, let's see how long it takes when we do our original example. So remember, our original example was x of t was sine of t, and y of t was cosine of t. Now, you may remember that when we found dy dx before, dy dx ended up being a fraction. So it's actually probably going to be quicker to use this formula for the second derivative. All right, so let's see here. So we have x prime. Well, the derivative of sine is cosine. Then we have y double prime. Oh, wait a minute. This wasn't cosine t. I apologize. This was e to the t. There we go. So we have y double prime, or the second derivative of e, but that's just e to the t. Okay. And then we subtract here. We have the first derivative of y. All right, that's another e to the t. And then we have our second derivative of whatever x is. So the derivative of sine is cosine. The derivative of cosine is negative sine. So this will actually turn to a plus sine of t. And on the bottom, we divide by x prime cubed. So x prime is cosine, so we have a cosine cubed in our denominator. All right, so there's our formula for the second derivative. And then let's say we wanted this at t equals 0 again at the same point. Well, then we would end up getting t equals 0. Cosine of 0 is 1. E to 0 is 1. So we have a 1 there. Sine of 0 is 0, so we don't have that. And cosine of 0 is 1. It looks like we also end up getting 1 for our second derivative as well. So once again, if we look at our little picture here, so there's the point. We know it has a slope like this. We also know that the function is going to be, or maybe not necessarily function, but this curve is going to be concave up at that point because its second derivative is positive. So whatever the curve looks like, it's going to look kind of something like this nearby that point. So it has a slope of 1, and it looks like it's concave up. So technically, you could use these to help you with your drawings if you want to make things more precise and know the ways the curves connect to each other. But you don't have to do that. You could kind of just approximate what's going on when you're drawing. All right, so that's everything we need to know about derivatives. And then I'm going to talk a little bit about integrals. Now, usually when we think integrals, we think area under the curve, right? But that's kind of a bit ambiguous when our curves can kind of like spiral around and cross themselves and things like that. There is a formula for area of a curve of parametric equation, at least for simpler ones, but we're not going to go over that. That's not as useful as what we're actually going to talk about. So let's say we have 2 points. Okay, right? So let's say the curve kind of goes maybe something like that. We have these 2 points connected by a curve, which can be represented with a parametric equation. So now let's say we wanted to know the length of this curve. So say this is maybe like a trail that you're following. We would want to know how long this is going to be. Now, usually when we figure out lengths, they're usually straight, but this curved one, it's a little bit strange. Now, what I'm going to do is I'm going to break this up into several pieces, and there's one, and then there'll be that one. And what I'm going to do is I'm just going to connect these pieces with straight lines. Like that. And what I'm going to do is I'm going to see how long each of these lines are, and then maybe that'll be a good approximation for how long this is. Although by looking at the picture, it's not going to be that great. So let's look at this triangle right here. This is our change in x, our change in y. Here we have our second x value and our second y value. And then here we have our third. Now, if we want to know the length of each of these lines, we just do the Pythagorean theorem on each one of these triangles. So we have root x1 squared plus y1 squared, and then root x2 squared plus y2 squared, and then root the same thing with 3's. All right, and if we add all that up, we'll get probably not a very good approximation. It'll definitely be an underestimate, but we'll get some kind of an approximation for this. Now, how can we make this better? How can we make the approximation better? Well, what we could do is we could just add more lines. So maybe they'll kind of more closely follow the curve. I bet if I double the number of lines for this, this would be a much better approximation. We could just keep increasing the number of these lines that we make. But remember, each one will be smaller along the way. So each of these x and y values will be smaller. And I think you can see where this is going. With integrals back in Calc 1, we kind of did this with rectangles, where we had more and more of them, but then they were getting smaller all the time until finally in the limit, we ended up getting an integral. So with this, we're going to get an integral as well. So we have the integral between x values a and b, and we have the square roots. So we're adding up a bunch of these square roots, and what is it the square root of? Dx squared plus dy squared. So this represents the length of one of these tiny little segments. We have a tiny change in x, a tiny change in y, then we look at the length that ends up making. So this is going to be our length. And as we go to infinity, as we have more and more of these, the approximation becomes more and more exact until it's perfect. Now, looking at this, it's kind of strange looking, right? Like we have two differentials in there, dx and dy, and they're both kind of mixed together. So how can we make sense of this? Well, what I'm going to do is I'm going to do the same thing that I did with derivatives. I'm going to stick a dt in here, but if I put one up there, I also got to put one down there. as well. Now, what's going to happen is that I'm going to move this dt into the square root. But whenever we move anything into a square root, it becomes squared. We have dt squared, and then we have this dt out here. And then finally, I'm just going to split up this fraction. So I'm just going to erase this. We're going to split that fraction, and I'm going to divide by each of these separately. So I have dx dt squared, and then dy dt squared. And this is the formula that we're actually going to use. We're going to use dx dt squared plus dy dt squared, since we're usually given those, and those are easier to figure out. And by the way, so here these were x values, but then these are going to be t values right here. All right, now what's the interpretation of this? Well, in addition to length, you can also imagine this as the distance that a particle moves from the first time to the last time. And we can imagine this as the integral of the particle's speed, and then we multiply by the time lengths. You probably learned that distance equals rate times time. So we have all these speeds times these tiny amount of times. If we add up all of those, it'll be a bunch of distances. And when we integrate it, we'll get the total distance. So that's what's going on if you like to think about things in terms of physics. All right, so let's see an example of this. These integrals can sometimes be a little bit tricky, so let's learn how to deal with those. I wrote down a good example so the integral wasn't too hard. We have x of t is 1 plus 3t squared, and y of t was, let's see, 4 plus 2t cubed. And we're going to see how far or how long this path is between t is 0 and 1, or in terms of physics, how far this particle moves between time t equals 0 and t equals 1. So let's set up our integral here. So we have the integral from 0 to 1. We have a square root. And then we need to know what x prime and y prime are. So x prime, well, let's see here. We just do the power rule on this, so we just have 6t. And then here we have y prime, do another power rule. There we have 16 squared. Now, one thing that's really easy to forget is that we need to square these derivatives when we put them inside the square root. So I'm going to square x prime, and I get 36t squared. And I'm going to square y prime, and I get 36 to the 4. Okay, so there we go. So this is the integral that we have to do to get the length. Now let's take a look at this. This looks a little messy at first, but one thing we can notice is that inside here, we can factor out 36t squared. We end up getting 36t squared times 1 plus t squared. And then when we move this outside of the square root, it becomes, we take the square root, but remember it's in an absolute value. So it's absolute value of 6t times the square root of 1 plus t squared. We kind of dealt with this situation back in calculus 1 when we had squares inside square roots becomes the absolute value on the inside or on the outside. Now we need to remember that again, because there will be some problems where the absolute value makes a big difference. Now in this one, any number we're going to plug into there between 0 and 1, those will all be positive. So in this case, we don't need the absolute values, but if we had any kind of negative bounds on there, we would need to consider the absolute value. All right, now we have this integral, which looks a little better. We see a root 1 plus t squared, so that kind of suggests trig sub, but I don't really like trig sub as much, so I'm going to try to see if I can do u sub. But u is 1 plus t squared. du is 2t dt. Ooh, that's almost what we got. We have 6t dt instead. So 3 du will be 6t dt, and you have a perfect match. All right, so let's write our new integral, which will be totally in terms of u. Oops, probably shouldn't have erased that one. 1. There we go. So our new integral, well, let's see, 6t dt, that's the equivalent to a 3, and then we have a du. And then we have square root of 1 plus t squared. That's just the square root of u. Now, one thing I like to do with u sub is I like to change my bound so I don't have to go back to t's. So for my bottom bound, I take this 0, put it into my u formula, and when I put 0 in here, I end up getting 1. So 1 is my new bottom bound. And then to get the top bound, I do the same thing just with the top t value. I'll plug 1 into here. I get 1 plus 1 is 2. Now, since I did that little arithmetic right there, I never have to go back to using t's again for the rest of the problem. All right, now we're going to do this integral, which this is definitely a Calc 1 integral at this point. So I have 3. If I raise this power by 1, I get u to the 3/2. Then I divide by that, which is the same as multiplying by 2/3. And this is from 1 to 2. So these 3's cancel out. So I end up getting 2 times 2 to the 3/2 minus 1 to the 3/2, which is 1. There we go. That's how long the curve is between t equals 0 and t equals 1. Now, one final little way you can check your work here is you need to make sure that this is a positive number. Displacement could be negative, but distance is always going to be positive, or maybe 0, but most of the time it's going to be positive. So we end up getting a negative number here. I would recommend going back and check to make sure you didn't drop any signs or anything like that, or maybe there should have been an absolute value in there that you should have used. So make sure that this is positive once you're done. All right, well, that's all I have to say for now. So let me know if you guys have any questions either on this or the homework that's due today, and I can help you out.